We'll still wait.
Yeah, we should, yeah. We have to wait till 7. It's only 5 to 7. Yeah. Actually, we could, let me. What do we have? We have to make sure that it's. I hope they know. Hey, Bibby. Bibby. You know how to do this because you use this more often.
Yeah.
That's what I'm saying. If I look at it on this.
This is perfect.
I want- no, I
People
want-
see that.
Yeah, but I want to
And then
see
you see
that.
the
I
next-
don't want to see the next slide. I wanna see
Okay.
just one.
Yeah.
Or I'm gonna play a
And-
PDF file instead.
You won't be able to see enough, just because this tells you like how to segue into the next.
Yeah, yeah,
And
yeah.
then you just use that and then use the arrow, right, which is really, that shows up really well.
Right.
Like, so sorry, David. Yeah, so
Yeah.
P, it's on the P right now.
Yeah, yeah.
Yeah, so I think it's kind of nicer. Should be out here.
Up here? Oh, it's
Or whatever. you
technology is whatever it is, but
But yeah, so you'll just advance it here, but, or we'll use these to advance, yeah. There's just so much smoother without pointing. So just, I would just use these keys, match original one. Save your changes, don't save.
just a minute. I just want to get out of here. Just a second.
Okay.
I want to get
Your screen sharing.
I want to do the PDF. You hear that? Okay, that's something I can understand. I can see what it is on here. So I was, just do that. Okay, so it's.
Yes, I think you have to go back to PowerPoint, because like now we see the Zoom window up there,
Right.
like you have to
Well, I
go.
want to do a
PowerPoint.
maximize the screen on. Wait, what are we doing?
You have to go to PowerPoint.
Wait, it was working. You want to show?
Well, I wanted to put it on PDF because the way it's set up in PowerPoint, you fix it up the way it is because it's kind of,
No, it was working before. Could we do PDF? PowerPoint? Because
Just an PowerPoint back. when-
They're on PDF, yeah.
what is PDF? But could we go back
This
to?
is, this is PowerPoint, isn't it?
No, this is.
Okay, okay, just don't.
Yeah, let's go back to.
Sorry.
Because on Zoom they would have.
Mhm.
I'm sorry, this whole Zoom thing is completely messed up my computer.
Because you need to, before I could see the second desktop. Okay, let's,
Again,
there's no second desktop right now. Wait, one second.
again, tell me about the retarded beam solution.
See the second desktop.
Can you explain that?
No, but it's not, because on Zoom then we didn't see or you could see the second desktop, not the. Because on Zoom they don't, like on YouTube, they see it there.
Well, maybe start sharing the screen again or something, just take it back to zero.
I mean, wait, there is a. Well, can you go back to desktop one? What you did before? Okay, I guess go.
Yeah, well, they're trying to get this PowerPoint back.
Okay, that's good.
Because the book that breaks down
Yeah, yeah.
the
Okay, desktop three,
kitchen.
and then. Share. Okay, share this one. And now,
Do presentation mode here.
yeah. It's, yeah, it's behind us, yeah. Lateral. Lateral. I hope on YouTube it's fine.
Okay.
I mean, it's fine, but it's on YouTube.
Okay, so that's fine.
It's like green balls.
No, yeah, but also difficult to do it. Yes. Because it's like, Stephen has here also. So I think it's because of this multiple decks.
Do you want me to shut down all the?
Did you change desktop? No.
Okay. I need to see the YouTube.
Okay.
Yes, but just bring the last one here. So right now it's based on this. So we have to share. So just give me a second. Nothing.
Oh, wait, yeah. But then that is a this.
Right.
By the way.
It's like-
It's like. What's in presentation? So maybe try to get it to another desktop. Because now your desktop over here.
So I'm going to desktop 4 or 2.
Which is.
Let's do the. Oh, the YouTube is. Okay.
Okay, go to the next slide. Let's see if the green stuff persists. If that's,
What is lighting?
No, but it's.
Is it still going to be presentation?
It's gonna be.
you've got an editing button. I think if we go to the next slide.
Okay, we're done. Okay. So you want to go to the next screen?
Yeah, well, it's just because I want to see if this green frame that you were complaining about is going to be on every slide.
Maybe go, yeah.
Yeah, because you've got something down at the bottom that has your editing.
Maybe, oh wait, maybe on the Zoom. Can you
Okay, well, it doesn't matter. Let's just leave it there.
layout, maybe layout? No.
Okay, we're doing the half-hour question and answer period. At the beginning. She's saying, how can I make this thing work? And I say, you can't. So that's how it's going, okay, in case you don't know what's going on. Well, one of the reasons I always show PDFs because it's, you can't break them.
So YouTube is fine, this is
What are
fine.
you trying to do now?
I don't know.
Before there wasn't this green line, so we're trying to figure out.
Oh, you want to get rid of the line?
With rooms like.
I think if the green line is standing between us and the clock.
Yeah,
I mean,
okay, let's.
This is the green line that I put on all my slides to promote ecological awareness.
Okay.
Maybe.
Okay, then it's 7:06. So is this?
What are you seeing on you? It looks good on YouTube?
Yeah, like YouTube is fine, right? Okay, YouTube is fine. I don't know why this is fine, but this is fine. Somehow presentation is not fine.
As long as I can go along and just change slides.
Yeah, like
Okay.
it's just like the green line will be here,
Yeah.
so but you can change it, if you want, and then,
Okay.
yeah.
I mean, we shared it correctly, right? We shared the.
Share the thing correctly, yeah.
Yeah, but she said if you share it. That's
You wanna come up here?
6 degrees, remember? There's that.
Let's take more than 3 services for.
Yeah.
Okay.
I kind of lost.
Yeah, that's what they would pause it.
No, it's shared. Okay.
No, if
No.
it was just share the PowerPoint,
the
the presentation mode will show up
Yeah.
here.
Not this one.
Okay, do it.
Oh my god.
Well,
So where?
It's all
Okay. I'm looking for good graduate students. Is that Good, thank you.
Hello, everyone. Thank you for the patience. So I also wanted to apologize that I noticed today that the screen is not working, so we will check on the screen copy. But yeah, it's my pleasure tonight to present Professor David Hanna, who's gonna give a talk on the HELIX experiment, which is a very exciting experiment, and I'm really looking forward to hear more about it. Just as a quick note, this is the first public lecture of this year. We're gonna actually have a second one at the end of October, so stay tuned at the end of this talk. And since we already lost some minutes, I don't wanna take more of David's time, so we can just jump into the public talk. Thanks.
Okay, thank you for the introduction. I'm sorry for all the technical difficulties, but what can you do? Physicists are not good with electronics or anything like that, also and computers. Anyway, so yeah, so here I am. I've got to have a few words from our sponsor first. So the first couple of slides, first 5 slides are from the Trottier Space Institute, which is and the McGill Physics Department, which is sponsoring these outreach lectures. And so
for 1 second to zoom again.
I don't know, don't touch anything. Why,
Can you go?
what is that?
No, because it's for you too.
Sorry, the thing is currently showing as pause. I'm so sorry.
So
You need to try.
I knew there was gonna be a problem when they didn't have the green M&Ms in the green room.
yeah,
Yeah.
we're not seeing it here, so we're trying to see it.
Okay. Why, we done?
Sorry. Does it change? So we might need to extend that Q&A session.
Yeah. Everybody make a wish. Okay, so I forgot what I was gonna say. Anyway, yeah, so basically the I'm getting a complete, I get the next 10 slides just by here, so I have to look up here. It's very inelegant, but we'll proceed. Yeah, this is a series of talks put on by the Trottier Institute, sponsored by Lauren Trottier, who sponsored this building, is sponsoring another building on campus, which led to the felling of one of our oldest and loveliest trees on campus. He supports the activities, and so does the McGill Physics Department. Okay. Yeah, so here's some stuff which I'm going to go through. These are all things like behave yourself. Okay. So, and we can only, again, this is stuff that we've used up too much time with that stuff. This will be at the end, so you can scan this and make your thoughts known to the people who put on the series. I just want to put in a little ad that the next talk is going to be coming up on October 29th by Professor Bruno Tremblay from this university, talking about Arctic climate change, which is it's quite interesting to me because I've just part of this talk, you'll see I spent a lot of time in the Arctic last summer, and so it's become increasingly relevant in my little world. But today I'm going to talk to you about the flight of the HELIX. I got the name from a movie which I highly recommend you see. It's about people who crash a plane in the Sahara Desert and eventually reconstruct it such that they can take off and fly back to freedom. There's been a remake, but I saw the original one back in the 60s. And that's what inspired me, because names with the ending in IX are kind of a common thing. HELIX is what I'll be talking about. I just want to say that, not that I'm bragging or anything, I'm just wanted to say that I have the lofty title of Rutherford Emeritus Professor of Physics. Okay, so I retired at the beginning of this year when I hit the magic age when you have to start drawing down your savings and so on. And I was a Rutherford professor before that. Now I'm the Rutherford Emeritus Professor. So that implies certain things like I have to, I'm contractually obligated to talk about Rutherford wherever I can. Okay, so that'll explain some of these slides. So I'm going to talk about this. This is the payload for the HELIX experiment. These are solar panels, and then there's the actual scientific instrument up there. And in Canada, we're sponsored by our Natural Sciences Engineering Research Council, as NSERC, And also the Canadian Space Agency is getting more interested in this kind of activity. And so they gave us a lot of money too, on the scale of things. But primarily the costs are borne by NASA. And NASA has a division called the Columbia Scientific Ballooning Facility, which actually organizes all the balloon flights, the scientific ballooning up in the stratosphere. And if it wasn't for them, there wouldn't be this project. I have to acknowledge that. And it's yeah, and we were all friends when we did this experiment. It was before Trump was elected, so it may not happen. It may not go forward from here on. But this is the team. This is these collaborations come and go over time, and so people graduate, people move on. These postdocs, some of them are not there anymore. One of the people back there, this guy died actually. But we're all standing around the payload a few years ago in the assembly area in the University of Chicago cyclotron. This is where Enrico Fermi built one of the world's first really big cyclotrons. It was really interesting particle physics back in the 1940s, and now it's hallowed ground, but that's where the Chicago ballooning people have been putting together payloads for years, and that's some of the people involved in the experiment. I tend to take too long fleshing these things out, so I better pick it up, otherwise I'm not going to finish on time. Introduction to cosmic rays, history and origins and experiments. People joke about me, but all the students and young postdocs say, "You're an old man." And I say, "How can you tell?" And they say, "Well, because you're interested in history, and I am, and I make no apologies." And I'll talk about HELIX with the scientific motivation, the technology that we use. And we've had one flight so far. We call it an engineering flight. That sort of means it didn't work as well as we thought it would, but it's a sort of a learning experience, and it's sort of proving to NASA that we're worthy of future support. And then the recovery, which was a real adventure up in the Arctic, and then the future prospects for the collaboration. Okay, so history of cosmic rays. Cosmic rays were discovered by Rutherford, of course. No, but the point is, they were discovered 100 years ago. In 1912 was the official discovery date, and the sources from which they come are not known for sure, but they are a very important part of astrophysics. Sometimes they're neglected because they're not something where you can have a picture from the space telescope or something, or you can stare up in the sky and see stars. It's all invisible. Cosmic ray particles are coming to you as we speak, but you will never know they're there unless you have specialized detectors. They're charged, and charged particles do not go in straight lines if there's a magnetic field around them. All over the universe, all over the galaxy, there are magnetic fields, very small magnetic fields, but nonetheless they will curve the trajectory such that you haven't got a prayer of actually saying, "Oh, I see one coming into my lab. It's coming along in a straight line. I can see it's coming from that star over there." No, because it's wandering around, and that'll become evident in the talk. However, we've been looking at these things for over 100 years, and we know the composition at low energy. Because we've been able to get instruments up into space that can detect them and measure them quite precisely. We know the energy spectrum all the way out to 10 to the 20th electron volts, which if you can't relate to that, just take a lead brick and drop it on your foot. That is the energy that's packed by a single proton, okay? And the proton will hit you like that. It'll just go right through you. You won't feel it because it'll just ionize a little bit, go out the other side. But if you could actually stop that energy, that's what it would feel like, or a really fast baseball pitch hitting you in the head or something. That's what those things are, a single elementary particle. So it's quite amazing. And the thing that I'm brought in, my background is particle physics. I went into particle physics as a young person and spent part of my career just doing straight up particle physics at accelerator labs. And that's essentially the father of particle physics is nuclear physics. The father of nuclear physics, in some ways, is cosmic ray physics, because that's where that was our big accelerator in the sky. So I'm interested in that aspect of it. Okay, so going to the Rutherford side, this is people started noticing around the time that radioactivity, that everything was being discovered. It seems like all of modern physics started around the turn of the 19th century, around 1899 to 1901. People discovered X-rays and radioactivity and so on, and people had no scientific instruments. They didn't have electronics. They didn't have any kind of transistors or even vacuum tubes or something. They had nothing except things like these old-fashioned electroscopes. I mean, you would take something with a couple of gold leaves, some really thin, flimsy, little bit of gold foil, hang it off a central conductor, and if you came up with a charged object and touched it, the leaves would get the charge and fly apart. That's great, and that's how Rutherford and his workers and competitors and so on measured a lot of things that having to do with radioactivity. But when they if they would leave them around, there's no reason for them to suddenly go back down to zero. Why would they? Why would they discharge? And the answer was they shouldn't. And so people would come back the next day or a few hours later in the lab and find it all disturbed. Big mystery, what's going on? So people like Rutherford and one of his collaborators, Henry Cook, made key measurements in this at McGill and came up with the idea that there was some kind of radiation that was discharging, that's coming into the residual gas in the object, in the electrometer and discharging it. And so the natural thing to say was that, well, you know, Henri Becquerel, people who discovered radioactivity in the beginning, discovered it in crystals and pieces of ore that they dragged out of the mine. So they said, maybe it's all underneath, you know, radiation is coming up back. And that's certainly true. There's a certain amount of that, and people prospected for uranium all over northern Canada, dragging detectors around behind planes and so on. So radiation does come from the ground. But there was a sort of an industry in trying to figure out, was that really true? And people did experiments. In fact, there was a guy who built a very sensitive electrometer and took it up the Eiffel Tower, trying to see a sort of systematic fall off with altitude. And he was unable to see any significant effect because the lever arm was not long enough. He wasn't going high enough. And also the precision of the detection wasn't good enough to see it. So it was just lost in the noise. So the person who really got, oh, by the way, this little, this is not a Trump coin. This is a Nobel Prize medal. And I just thought I put that on, since this is Nobel week, there's a way to sort of recover from my serious disappointment on Tuesday morning. I put all that, I sort of flag all the people who have so far gotten Nobel Prizes in physics. Okay, so every once in a while you see this little gold disc, and that's to show that the person involved was a Nobel Prize, not necessarily for that work, but just that these were people who were Nobel quality people who had an interest in this field. So therefore, that makes it worthwhile, and that makes me worthwhile. You see, so that's the rationale. Okay, so the first person to really get going on this was a fellow named Victor Hess, an Austrian physicist working he got a job at the Vienna Radium Institute, which was a very famous, one of the big three labs, Cambridge, Paris, and Vienna. And he got the idea to go up in a balloon and up to 5 kilometers, which at the time was a pretty daring thing to do. And he took up a few of the best devices he could find, and he went up 5 kilometers and saw that the rate was going up. It wasn't going down. It wasn't like he was getting far away from the radioactivity in the Earth. He was actually approaching the source. And so the conclusion was that it came from outer space. And like everybody looking for a Nobel Prize, he did this when he was young and lived long enough for the people in Sweden to get around to it. Give him an award. So one of the people who jumped on this was a guy named Millikan. You may remember him from the charge, measuring the charge on the electron with his famous oil drop experiment. He had a great theory. He was a big fan of this and a big interest in cosmic rays, and he thought they were gamma rays coming from atoms, the birth prize of atoms, called them. And so he was convinced they were gamma rays without much evidence. He drew this conclusion, and he had a student, Arthur Hawley Compton, the man who got the Nobel Prize for the Compton effect, the first example of quantum physics in the lab. And so they duked it out. You know, they were both Chicago people at the time, and they had quite a public argument for a few years. But Compton prevailed in the end because the thing that could show that they were charged was that the Earth is like a giant dipole magnet, and there's structure in it, and so there's all the particles coming in near the equator get deflected, and that's one of the reasons we're still alive. And up at the poles, the intensity goes way up because there's no magnetic field to protect us from them. And it's a true fact that people who work in the airlines, particularly female flight attendants who spend a lot of time flying at high latitudes, are not allowed to fly. They get dosed up. I mean, they're like nuclear workers at some level, you know, and if they're pregnant, they're no flying at all. See, so it is a true thing that flux varies over the Earth, and that shows you that they're charged particles. Okay, so that was a big thing, and then Millikan, who, you know, nonetheless had a great reputation. He moved to Caltech and started people working on cosmic ray experiments, and that led to the discovery in 1932 by Carl Anderson at Caltech. He was one of Millikan's students, and he won the Nobel Prize for discovering the positron using a thing up on the left. That's a picture of a curved track. That's a cloud chamber. It's a sort of, you've heard of bubble chamber. The cloud chamber was sort of the father of the bubble chamber. If you haven't heard them, it doesn't matter. There's visual detectors which can show particles. And this is the kind of, instead of having those gold leaf electroscopes, people are starting to get now particles, you know, devices which would actually show the existence of a particle when it's being detected. This is the smoking gun picture to show that he had discovered a positron. And he was also active. He worked with Nettermeyer, his student, a few years later, and discovered a heavy electron called a muon. And so that was a great discovery. And then in just after the war in 1947, people in Britain were using essentially photographic film. You know, all you kids with your digital cameras have no idea what I'm talking about, but that's a photographic film. It's plastic with a bunch of chemicals on it that make pictures. And the thing is that they can, if you expose them to cosmic rays, the individual grains in the emulsion that's on the plastic get darkened by the passage of a particle. And so here we see the prize-winning photograph of a prime meson coming in, decaying very quickly, and then off to the side, it's one of its decay products, the muon, which is charged. The other decay product is a neutrino, which is invisible. You can't detect it because it has no charge. So this is another triumph. I'm an experimentalist. I love this stuff because it says we make advances in physics, not just by sitting around theorizing. I mean, that's a beautiful thing, but you know, without experiments, people need to be reading in, you know, and you know, the dialogue, the sort of dance you have between theorists and experimentalists is what keeps physics viable. You know, you make an experiment, explain that, and they explain, you say, my explanation implies that if you do another experiment, you see this, and you go back and forth. So this is the kind of thing that was going on in cosmic ray physics, but it was new instruments. Instrumentation was essential to to that. Plus high altitudes. This emulsion was exposed at the peak UV in the Pyrenees, and Anderson and Milky had all their apparatus picking up high peak in the United States. So high altitude, because that's where the cosmic rays are. Okay, so just to say, there's peak to MIDI, 2877 meters in the French Pyrenees, and then the Jungfraujoch in central Switzerland, right by the Eiger. And this is a great time. You know, if you're a physicist, I mean, I was born too late because, I mean, basically what you could do is you could go over to Switzerland with a stack of emulsions, leave them there, ski out for a week, come back, pack it up and go home, and then give it to a bunch of people to scan, you know, and if that isn't the sweet life, I don't know what is, you know. So and you know, having other people pay for it. So this is the kind of thing that they were doing, and it all came to an end because coming back, using all kinds of technology that was developed during the war, the Second World War, people advanced the art and science of accelerators to the point where they could build synchrotrons, which are the ones capable of reaching the highest energy state. So that's the first operational synchrotron. It was a 3 GeV device, 3 times the mass of the proton is its energy, and it was the one that could produce things that had only been glimpsed in very low numbers, very infrequently, in totally uncontrolled experiments in cosmic rays. They can now make them routinely in the lab, which is what the thing you want to do as a physicist. You want to make measurements. So that's the positron. It's down at Brookhaven National Laboratory in the US, just outside New York City. And yeah, so that was when everything switched over from working up in the mountains to working in the lab. And this is the it was called the cosmotron because it essentially took over the role of cosmic rays. But the other beautiful thing is that once people got to know enough about particle physics, they could understand more about what was going on in those cosmic rays coming in from outer space. Okay, so another discovery, this is the discovery of extensive air showers. It turns out, and I have a couple of students who have come here without me having to, I have no influence on them anymore, but they actually turned out, but they were my summer students a couple of years ago. And I showed them, I said, look here, you take a scintillator here and a scintillator there, like two counters, which when a muon goes through them, they will make a pulse on the oscilloscope. So I said, watch, if you do this, you put them one on top of the other, you see, you have a trace from one phototube, one trace from another, you see them, two little blips simultaneously. You take them apart, no more blips, just one or the other, but not together. Okay, so this proves that one particle goes through, but the cool thing that Pierre Auger did up on the Jungfrau yacht, he took them apart anyway. He said, let's just be patient. And you know, instead of getting the sort of 1 or 2 per second, he was getting 1 or 2 per minute, but they were still firing. They moved a little further apart, and then it was getting 1 or 2 per hour. And the whole idea was, yeah, you are getting coincidences, but not from the same particle, but from the same event up in the sky, which is producing more particles coming down, and that's called an air shower. And so this is the cartoon of what it looks like. You have a primary particle, which is the say an iron nucleus coming in as a cosmic ray, and then it hits the nitrogen in the atmosphere, and these things break up. You know, gamma rays are produced as nuclei de-excite, and you produce pions. If you have enough energy, the pions decay to muons and neutrinos. All of physics goes on in these things and streaming down towards the Earth at the speed of light, and that's called an extensive air shower. Just a little piece of trivia here. Auger spent part of World War II at the University of Montreal. He was a member of the French delegation in the so-called Anglo-Canadian Atomic Energy Lab that was produced over on the other side of the mountain, which was largely filled with Frenchmen at some level. I mean, there were a lot of people from Curie's group that had escaped to England, moved to Canada, and so on. But he was not one of them, but he was part of the French scene, and they sent him over to work on this. I found out when looking up the details on this, he's actually credited with giving Charles de Gaulle the secret of the bomb. Not that Charles de Gaulle made one, but basically, you know, he spent World War II in London as head of the Free French, but you know, everybody tried to keep a lid. I'm assuming everybody's been to see Oppenheimer, but Goebbels tried to keep a lid on everything, and this guy just blew the lid right off as far as the French were concerned. They learned about the bomb. Stalin learned a different way, but so Pierre Auger is quite a figure, and you'll see his name coming up pretty soon for another application. So here's the air shower physics and its implications. So now we know that high-energy particles coming to hit the upper atmosphere and engage in all kinds of interesting nuclear and particle physics interactions. So you end up with a giant spread of particles coming down on the ground. And so when you come down to sea level where we are, everything is either a muon or a neutrino, and everything else is decayed or been absorbed coming through the atmosphere. And that's the reason that if you want to detect the primary particles, you want to detect beryllium, which is what we do in HELIX, you have to go up into space or as close as you can get to space, the top of the atmosphere. If you want to detect short-lived particles, you have to go to high altitudes. And there's all these people that do low background experiments, people trying to look for proton decay or double beta decay without neutrinos, dark matter. They all have to fly deep underground to be away from this range of particles. Okay, so that's why people are going down to well, Snow Lab is very famous. It used to be one of the deepest mines in the world for doing physics. That's where the Nobel Prize for Art and Technology came from years ago. But the Chinese have got something even deeper and bigger, and they're going to take over. But that's why people are hiding out underground. It's because of grace. Okay, so here's a complicated graph. I'm just going to jump through it. It's essentially just a plot of the number of particles in the shower versus depth. This is up at the edge of space, and this is down towards sea level. And each one of these curves represents a different energy. But the idea is that as you go up in energy, by the time you get to the Earth, you've still got plenty of particles in the shower. You've got millions of them spread out over thousands of square meters. So you can build a detector which is doesn't have to detect the whole thing. You just have to sample it. You can, if somebody says, "What? How much rain is coming down?" You don't have to go out and get a giant swimming pool and measure every drop of rain. You just get a cup or something like that, and you can scale it. by sampling it. So you can, the particles are all coming down in a thing called a disk, which is, actually a little bit bent from the geometry of the situation. Those are the particles. They're coming down, they're hitting these counters here. And with measuring the charge deposited in the counter and the timing of the counter, you can actually find out what direction it came from and how much energy was in the shower. Just because there's so many particles to help you do this. And there was a big fad back in the mid-80s when I started working here at McGill, was to build air shower arrays to do gamma ray astronomy. And this was motivated by some bogus measurements that we all got seduced by. And so this was my thing. I built this 19 counter array right at my startup process when I got here. It's quite possibly the reason I hired me. You see, kind of trained me at the time, but boy, were they. Anyway, I've retired now, so I can fess up on that. But anyway, so that was, but it was something that went and kept on going. It wasn't like people sort of, well, that's a silly idea. They just said they're not big enough yet. Let's keep bigger and bigger. So now we have the Pierre Auger Observatory, the world's largest detector. It's located in Argentina. It's 3,000 square kilometers, which is, they show it on maps of Belgium and stuff like that, just to show how big it is. And 1.5 kilometers between each counter. The counters are essentially a great big barrel of water detecting Cherenkov light put off by the particles as they go through. And it's been running for almost 20 years, and it's making measurements at the very high energy end of the spectrum, a place where you only expect a very few number of particles to come in. You see, so there's the one that's covered by the Auger detector, and the competing one in the US, in Utah. And these are the ones where satellites and balloons do the job. And yeah, with all those different detectors, we pretty much covered the whole energy range. We've got this really nice measurement. And the people in the condensed matter theory go crazy when they see something like that, because they love power law spectra. I don't know why, but they do. And this is like one of the longest power law, even though there's a little bit of a bend in it called the knee. This is a beautiful power law, meaning it's a straight line on log scale. That's technical. But so the idea is that with air showers, you can get long exposure times. You can run the experiments for years. You have large areas. Balloons, you have shorter exposure times and slightly larger areas than you do with satellites. But satellites are the ones where you can make the cleanest measurements, but they have to be small. You have to get them into orbit. So there's a bag of tricks, and they've all been used, and that's our understanding of the energy spectrum. There's a couple of examples. I just want to show this one here. This talk about ANSR2 in a minute, but this is an example of one of the ones that's gone around. The technology is there now. The ballooning is so good that they can put one of these things up to 40 kilometers altitude, and it'll circle on the polar vortex for up to 2 months without needing to come down. And so it's almost like having a satellite. I mean, because a lot of these things, when you have a steep spectrum, you say, I can go 10 more, I can go for 50 days. Well, I can go for 500 days. And the only thing you do when you have a steeply falling spectrum is you get another point at the very end of the spectrum. It's not like you can it's not transformative, so this is a pretty sweet thing. So why fly poles? Well, one is you get, during the ballooning season, you get 24 hours of daylight. And that means that you can run your solar panels and all your electronics off the solar panels without having to shut down at night. And the real reason is no reduction in altitude at night, because what happens is when people fly out of Timmins, they fly out of Mid Lake, Manitoba, they fly out of Palestine, Texas for a 24-hour test flight or so, because they go up and the balloon is up at 40 kilometers, and then the sun goes down. There's no more warmth of the sun, and so the gas starts to cool, and the balloon shrinks and the thing starts to go down. So what they do is they take up some ballast with them, and they jettison the ballast so the thing stays at the same altitude. But you can't do that trick more than about once, because otherwise you're just taking ballast up. So if you go in the poles, you can do it as long as you like, and as long as the balloon stands up. Why don't we do it in the north? Vladimir Putin, so it's basically, you heard about that Chinese spy balloon that was shot down by the American Air Force on our behalf. Same idea. The Russians are nervous about people having balloons fly over them, even though we say to them, and as scientists to scientists, they totally get it and everything, but it's just one of those things we have to live with. Okay, so here's a slide with showing that not only have people measured the spectrum of all cosmic rays, they've actually been able to separate them out. And this is a detector that was put up a few years ago. Very simple detector, but you can see, I won't go into it because I don't have time, but basically that plot up there shows you can actually see with just a couple of simple measurements from a very simple detector that you can identify all the different elements, and you can plot them on this graph. So that was so that's great, and so that's the sort of the experimental data. So where do they come from? Well, the smart money is on they probably come from the galactic cosmic rays, presumably come from supernova explosions. Now supernovas, if you haven't heard about them, are the end of a star's life. When the star is sufficiently massive, stars proceed starting off with primary ingredients like protons. Protons fuse to helium, helium fuses to the lithium and carbon and things like that. And sooner or later, everything fuses and fuses because as you fuse, you keep generating radiation, and that keeps the star in balance. But as soon as you run out of fuel of that particular species, the balance is ruined, and as the star collapses a little more, things get hotter in the center, you start fusing the heavier element. Because every time you fuse things, you get energy coming out, unless you're trying to fuse iron. Once you get to iron, it's a losing game. You can't fuse iron and get energy out. You only fuse iron by putting energy in. So when the star develops an iron core, the whole star collapses because all the bookkeeping is gone and all the balance is gone. And so the thing explodes. It's a complicated thing, but it's an observational fact. But again, people have been able to simulate this on computers. But so the thing blows up. But I want you to look at the layer structures. And so at the end of the star, like you have all these layers, which depend a little bit on the initial mass of the star. But essentially, it's an onion filled with different layers of nuclei, and those get blown out into space and become what we're made of. This is like physics according to Joni Mitchell. We are all stardust. And that's certainly true. But the thing is, look at this: hydrogen, helium, carbon, oxygen. There's no beryllium. I want you to note that there are certain elements which are just not made by fusion in stars. Here's an example of a supernova exploded in about 1667, according to records at the time. That's what it looked like back then. This is what it looks like now. And this is just a simulation. But what I want you to notice is there's all these filaments here which are glowing, and those are shocks. This is when the material from the explosion is heading out into space, sweeping out protons. Or deep space, big vacuum of space, you actually got about 1 proton per cubic meter in it. So if you just have a bunch of stuff flying through space, they're eventually going to collide with all that stuff and sweep it up. So again, it's one of these things like on a human scale, it's not much, but integrated over enormous distances and times and everything, it amounts to something. So these are filaments which are glowing because there's the hot stuff going on there. Those are the shocks. And then that's where we think cosmic rays are accelerated. Okay, so this is Enrico Fermi, one of the Nobel Prize winners in the talk. He was a professor at the University of Chicago, and as you know, he built the first operational nuclear reactor in the world. He also discovered an enormous number of things, built the Chicago cyclotron. Just a fantastic physicist. He invented, whenever you had a problem, you just go to Fermi and said, how are cosmic rays excited or accelerated? He said, let me tell you. And he would write something down, and it would be more or less right. So that was the theory that went along for a long time, was his theory that essentially you have these clouds of gas moving through the universe, and a particle would go in and encounter a magnetic field and get turned around. And just doing the statistics of it, you could say that if something comes along with velocity v, it'll eventually spit out particles sometimes with greater than v and sometimes less than v. But at the end of the day, you'll end up with a spectrum that looks like v minus 2. That's the power law that we have to explain. So he had a great explanation, but another one came along, and this is what these filaments are all about, is the idea that most of the particles get accelerated in supernova shock. That wasn't known back in the day of Fermi. A lot of the supernova phenomenology came along later, but these are the two leading mechanisms. So that's something that's coming along. Okay, so we have a source of particles, cosmic ray particles with certain energy, and that's in our galaxy that comes from supernovas. So we have about 3 supernovas per century. in our Milky Way Galaxy 3. I know this number because I actually proposed at the young person just after that air shower experiment. I proposed to build a neutrino detector to detect the neutrinos coming from an exploding supernova. And it came down that you would have to wait at least a century or so to catch one. And in fact, one went off in 1987, very famously, after I made that proposal, but I didn't have the funding to build the detector. But anyway, that's the sort of thing. I said, can we do it again? No, and they said, well, wait about 50 years, you might get another one, you know, so I gave up on that. But the thing is, it's okay because our galaxy is older than a century. Cosmic rays have been produced for more than a century. Everything is, you know, if you put this on an astrophysical timescale, that's pretty good. And so what our main problem is actually now is that we have 3 per century producing a flux of cosmic rays, which you can calculate. You measure it, you say, well, how many cosmic rays should be in our local neighborhood now? You say, oh, that's not enough, because if they just go off into the deep space, you know, there's not enough supernovas going off to produce the density that we see. But if you say, no, they're somehow trapped and recycle, we can do it. How do you trap them? Well, the only thing in the physicist's toolbox for making traps is the magnetic field. So you say, somehow the galaxy has a magnetic field. And it is mostly a dipole centered around the spin axis, and there's some random ones around from the effects of spinning stars and so on like that. So there's this kind of messy model which is being built up, and everything is messy now in cosmic rays. So we're not looking for a single beautiful photograph of a new particle. We're looking at calculations and Monte Carlos and stuff. So it's kind of messy, but this is the only game in town. So this is the idea that we have a galaxy which could be approximated as a big cylinder with a magnetic field, and the supernova is blowing off all these particles. The particles are being contained and leaking out very slowly. How fast do they leak out? We don't know. We have to figure out these things. And how do we do that? We make measurements like we make with HELIX. Okay, so it's you're grown-ups now. It's going to get tough. No more easy answers. And so we need experiments to resolve differences and guide improvements to models. Okay, so it's not like I am measuring the mass of the finite. That's what I went into physics to do. It's been done, not by me. And but the thing is, you don't get a clean answer out of this. All you get is that, oh, so and so is Monte Carlo or model is better than so and so else. So that's what we're doing with HELIX. And how do we do that? We use isotopes. Okay, so here's the quick course in isotopes. This is isotopes were invented by Frederick Soddy, who was an assistant of Ernest Rutherford here at McGill. He's a chemist. But Rutherford let him into the lab for some reason, and Soddy went back to England and discovered the concept of isotopes. Now, isotopes are just the same nucleus. The nucleus, the charge on the nucleus, the number of protons determines the charge on the nucleus, which determines the number of electrons attached to them. And that gives you all the chemistry. So oxygen and nitrogen are different because they have a different number of protons and a different number of electrons. That's what makes all the different elements. But if I come along and add an extra neutron to any of those, I don't get different chemistry, I get different nuclear physics. And of course, the most famous example of that is uranium-235 and uranium-238. That's the whole thing about enrichment for making nuclear weapons. It's the same chemistry, so you can't separate them easily. You have to have centrifuges, you have to have, you know, complicated devices. And whereas plutonium, you can't. That's that because it's a chemical thing. So carbon, you will all have heard of carbon dating. So carbon comes in different isotopes, 12, 13, and 14. 14 is unstable with a 5,000 year, 6,000 year time half-life. And so that's ideal for dating things if they're of the order of 1,000 years old, or 10,000 years old, or 1,000 years old. And for example, the Shroud of Turin, they did that. They were trying to figure out the age of that. For us, beryllium comes in a large number of isotopes. The ones we're interested in are 9 and 10. 9 is stable. 10 has a half-life of 1.4 million years, which is about the same order of magnitude as it takes to cross the galaxy at a speed of light. So it's an isotope which can be used in the same way that carbon-14 is used to date things. It's a way to measure things in the galaxy. So that's what we're doing. We're looking to make measurements on beryllium. Okay, so here's the why are we measuring beryllium isotopes? We're measuring it because all isotopes are created not in the star. Beryllium is created on the way here by carbon, oxygen, nitrogen. The things that are heavier than beryllium are zipping through the galaxy on the way to us, and they run into a proton. So the proton chips off one of the protons or nucleons in the nucleus, and then not only is it a little bit later on, sooner or later, you've got the lighter elements like lithium and beryllium, which are not made in the stars, but are made by what are called spallation reactions. So the thing that we know is that if they're made that way, they all were made at the same time. So beryllium-9 and beryllium-10 were effectively made in those collisions at the same time. Therefore, if they're both, if you have two that are made at the same time, one's 10 and one's 9, the 10 is eventually going to decay away. So it won't be there when it comes to the Earth. And so you will by the ratio of the beryllium-10 flux to the beryllium-9 flux, you can get a handle on some of the parameters of these models. And right now, the data in these models, the data that people use to tune up their models consists of these black points. It's huge error bars. So essentially, there's nothing going on. You don't have any real data. And so we're trying to fill in the gaps. We're going to, Helix stage 1 will bring in points that look like this. And Helix stage 2, which is further in the future, would be take it up to higher energies. And these two curves, the red and blue, are sort of sample models of what might be the right answer. So if you're trying to separate the red from the blue, this one's obviously favoring the blue model. So that's the goal. Why are we doing it, and why would anybody give us money to do it? Well, because we have a spectrometer which can resolve beryllium-9 and 10. This is beryllium-9, and this is beryllium-10, just assuming a certain ratio. Assuming there's a smaller admixture of beryllium-10 to beryllium-9. That's what it would look like in our data. This is a mass plot, and the way you measure these, you see that. Well, how do you know this is beryllium-10? Well, it's because it has a mass of a beryllium-10. There's 10 atomic units of mass, and the way you identify an isotope is you measure its mass. You measure the momentum, and you measure the velocity. P is equal to mv, so mass is equal to P over v. That's how you measure it. And how do you measure momentum? Well, you measure it in a magnetic spectrometer. Here's a famous picture of an event in the SLAC LBL detector where they won the Nobel Prize 50 years ago for discovering a particle called the TSI. And this is, they love to show this one because it's actually signed its own name. It's the side. And so Helix is designed to have a mass resolution of 2.5%, so we can make these resolved measurements. The reason we're even in this game is that there was an experiment proposed by Sam Ting, who was a famous particle physicist who got into astrophysics and built a $2 billion detector, which is now up on the International Space Station. And up until a few months before it was launched in 2011, it had a superconducting magnet. Now, the thing about superconducting magnets is they're very finicky. I mean, the ones in the MRI units are pretty much well understood and well engineered, so they don't quench. But the superconducting magnets that are at the edge of technology often just going along all of a sudden, and something will happen, a little glitch in the system, suddenly the whole thing will go normal. Like the superconductivity state will be destroyed, and the whole thing will just blow off of all the liquid helium being used to cool it, and that's the end of the game. And so they couldn't get their magnet to perform reliably enough to be able to send it out into space for many, many years. So they quickly changed the situation around. They had a spare from their prototype. They had a permanent magnet, and which doesn't have anything like the power to do the bending of the tracks, but they reconfigured it. And so it does pretty good physics for most of its measurement, but it can't do the resolution of separate isotopes. Okay, so this is what they've had 10 years of data, and this is what they've got. They've got three beryllium isotopes. That's what they're fitting, these three different curves, but that's their data. And you can say, well, that's great, but it isn't. It's got huge uncertainty on because you can change the fraction of these curves a little bit one way or the other and still get a pretty good fit. And so it's not a good way to do it. And so they pretty much left this one door open for other people to get in on. And so so that was known when they went up into space in 2011, and my colleague at the University of Chicago said, look, this is something we can jump on. We have a superconducting magnet sitting in the lab, left over from another experiment. And so this is the HELIX detector. The idea was you build a sort of a particle physics detector that you float up on a balloon based on a superconducting magnet, a particle tracker. So you can plot the trajectory of the particles going through, and you can see how much they bend in the magnetic field and learn what their momentum is. And then you've got these two big black things, which sometimes coming out very black, to measure the time of flight. The pieces of simulator that produces a pulse here, another pulse here, a couple of nanoseconds later, you divide by the distance, you've got the velocity. And so that's the HELIX experiment in a nutshell. There's the time of flight. I'm going to skip over that. The thing that I've been involved in most intimately with this experiment was to build the ring imaging Cherenkov detector. Like Cherenkov radiation was discovered by Pavel Cherenkov in Russia, in the Soviet Union in the 30s. And basically it's a blue glow that you see. Sometimes you'll see these spooky pictures of reactors and you see the glowing blue water. That's Cherenkov radiation. Particle goes through at greater than the speed of light, and it ends up producing a sort of a shock wave of light, which is essentially a bunch of photons going off at a given angle. And the angle, if you let the thing land on a detector, it'll form a circle, and the radius of the circle will tell you what the velocity. And that's called a ring imaging Cherenkov counter. And so where does the light come from? It comes from a radiator. You have a thin layer of material, which I'll get to in a minute. The detector plane is actually in the HELIX detector is made from silicon photomultipliers. These are silicon, little bits of silicon which can detect single photons. They're everywhere. They were invented about 20 years ago. Now they're just everywhere in physics because they're cheap, they're efficient, they're insensitive to magnetic fields, which is important for our experiment. They operate at comparatively low voltages. The only trouble is they're very noisy at room temperatures. Okay, so we have this detector made out of aerogel. The radiator, most Cherenkov counters were based on things like water or plastic. An index of refraction around 1.3, 1.5. That was good for particle physics in the early days, but for us, we want something which is not that. We want to have, for higher energies, you got to go to lower refractive index so you don't get polluted by signals from low energy particles, but you don't want to go so low, which is what you get with a gas radiator. So we have this thing which was invented for this is perfect. It's called aerogel, and it's silica aerogel. It's just it's a transparent medium. If you pick it up, it feels like there's nothing there. It's called frozen smoke, the nickname. And so we had this collaborator in Japan at Chiba who made a whole bunch of these things, and we got them and we took them out to we had to calibrate them. They're nominally they're flat, but they're not. So we had to measure the flatness, and then we had to measure the refractive index. And all of this was done by McGill students and postdocs. We built this electronic detector made out of CCD chips, where you can see these little radial lines. Each one of those is a linear CCD, which will measure the radius of that blue set of points. Those are photons. Well, this is a simulation, of course, but that's how the photons would land. In order to get the centroid of all those photons, we use this line of CCDs, 16 of them. And so that was built here in McGill. We took it up to Ottawa. I worked at Ottawa before I came at the National Research Council before I came to McGill, and they have a 35 MeV low energy nuclear physics kind of electron accelerator, perfect for the job, and absolutely not unused. So we went up there, and we meaning on the boss, I sent them up there, and I helped them set things up. But in general, they made 14 multi-day trips just before the pandemic shut everything down. But they managed to measure beautifully. We have the most precisely measured aerogel tiles in the world. Not that there's a lot of competition, but okay. So this is I'll skip this. This is the tracker that we used to stuff inside the magnet. But we were held up by the pandemic. You know, part of this thing was going on. We couldn't have meetings. We couldn't build the detector. We got most of our stuff done here at McGill before the pandemic shut us down. I spent a lot of the pandemic analyzing the data from those tests, but, when we came back, everything was going back. We said, okay, when do we go to Antarctica? I mean, that was the reason I joined the experiment. One of my young colleagues said, come join the experiment. You're good with hardware. Plus, you've never been to Antarctica. You want to go? Sure. You know, so, and, you know, didn't get to go. I went to Sweden instead because, you know, there's such a lineup in McMurdo, which is the place they launched the balloons in Antarctica. We were going to wait years to get a slot. Plus, getting the liquid helium down to run our magnet was going to be a problem. So we took an offer to fly out of northern Sweden, which is where the Swedes have a European Space Agency lab there, where they launch rockets and balloons, and on the way there from the town of Kiruna, which is it's reminds me of northern Ontario. It's like this mining town, and who would ever live up there? And it's because it's got the world's most productive iron ore. This is where Sweden got all of its wealth, was selling iron all through the 20th century. Anyway, the Sami, the local indigenous people, also are up there, and they have reindeer, which are free. You're not, you go to jail if you have reindeer, and they're all over the place. And everybody has extra headlights on their cars for long nights, so running back and forth. So we ran into a ranger just goofing off down the road, and so it was a lovely experience. Went over there, and we unpacked our detector, which was bottled up in a seagoing container in Chicago, taken down to Palestine for final tests, then put on a boat. This is all in January, and they came out in late March in the Kiruna. And I took over our beautiful, lovely, my little babies, aerogel tiles in my personal luggage, flying over to Sweden, and I put them in the detector, you know, the little encasing thing that we developed, and these are two graduate students putting shoving it into the slot that we reserved for them. So that was us assembling the detector. And it was launched on the 28th of May of last year, 24. And you know, we had a whole bunch of competition. There are all these people preparing their balloon payloads, but if you're sort of ahead of the crew, you've got your act together, you've got everything ready to run, you say, okay, you can come out now and do it. And normally what you do is you go out, and you stand around, you fill up the liquid helium, and stand around and check all the computers, stand around, and they say, we're going to scrub the mission. I mean, if you ever watch these things at NASA, you're like, we're scrubbing the mission for a week because you know, didn't feel right. You know, so that's the same thing with ballooning, and we got off on the very first day, the very first try. I mean, it's beginner's luck for me or whatever it was, but I wasn't there. I'd gone home by then, but I was getting bored because I put my part in. Anyway, so these are the pictures of the launch. Beautiful thing. And I have a couple of videos that I got from NASA, but I'm not going to play them. There's the path. Okay, so the first thing is it went up and it started heading towards Russia. And then the winds changed and it moved around. So there it is going across Greenland. 6 days later, it lands in Ellesmere Island. 6 days, 8 hours. And that is a picture from a GoPro that one of the grad students mounted on the payload. So it's like, you know, tell me you're not on the space station. Looks just like it, right? You're in space when you're out here. And that's the important thing, not to have too much of atmosphere. You want to get the stuff in before it hits anything in the atmosphere. Okay, so just to show you that there's actually quite a large number, this is integrated over the last 10 years or so, the number of paths that have gone over Greenland on their way to northern Canada. You probably didn't even know this. People are landing balloons on our territory. Can you imagine? You know, this is why we have to improve our Arctic military capabilities. You know, we're being attacked from Sweden, and don't tell me they're neutral. So this is where we landed, and it's the second most northern thing. We didn't break the record, but there was one smaller payload that made it 30 kilometers north of where we were a few years ago. But this for me was I just love this because I'm 71 years old, you know, and I don't have much time, and I've never been. You know, I consider going up to Laval to be a trip to the north. You know, so like most Canadians, I hug the U.S. border and watch American television. So the thing is, to actually go up and explore Canada's Arctic is way better than going to McMurdo, you know, which is a bunch of polluting things and stuff down there. So this is what we did. We did the recovery expedition. This is me up there, and this is our payload. Actually, that I found, I don't know where that came from, but it's I think the Russians photoshopped that or something. So this is what we've got. We've got, I think it's kind of 10 minutes. Okay, so this is where the payload was. And this is Yellowknife. This is the last place you can drive to. Well, you can drive over in the Yukon territories, but this, if you're heading up in the Northwest Territories, Yellowknife is where you can take a truck. And we had to get all of our stuff up there and then back. And that was the story of our recovery expedition, which was quite an adventure. And we used 4 different kinds of aircraft. Basically, because each one had its limitations on range or what kind of a runway it could land on, and how much cargo it could take. And so we ended up using all of those things in various combinations. I don't have time to go through that, but and here's the Yellowknife. If you've never been there, I recommend going. It's becoming a tourist spot now. Like for people, a lot of fancy hotels are being put up, mostly for people to go and watch the Northern Lights. A lot of people coming from Asia and so on to watch Northern Lights, but it used to be for miners, and it's a sort of jumping off space for people who want to do stuff from the north. For us, it was advantageous because we had a giant Canadian Tire in a Walmart, and in fact, all my American colleagues, they were talking amongst themselves. It's just this Canadian Tire. I think it's a Canadian Walmart. Because, you could just buy anything there. We went out, we bought ladders, we bought chop saws, we bought come-alongs, and things that we thought we wouldn't need, and we ended up needing. So it was great. So we stacked up all that stuff. So we emptied out our seagoing containers. We brought them to Yellowknife by truck, and we had all the recovery gear in them. And we started making it up into little kits, and we put them on planes. And we got, it's much more detailed than this, but I gotta go fast. So there were 5 of us in the recovery team, and getting people here and there in that small Cessna, and half the time people would go out to as far as one of the towns like Resolute Bay, and they'd have to turn around, like the boomerang, as they call it, because they get there, fly all the way there, and they couldn't land because the place was stocked in. And in fact, once we got in the plane, the pilot said, "Bring your passports. We may have to go all the way to Greenland because we won't have enough fuel to come back," or something. So it was a bit sketchy, and so I ended up going to Cambridge Bay on a commercial airline, Canadian North, and I just want to say there's a little bit of history here, and that's something I learned. This is Cambridge Bay. It actually came into being because of the DEW line. Some of you may have heard of the DEW line, distant early warning line, and it was put together. Well, by the way, it was the last of 3 lines, because during the Cold War, everybody's afraid the Russians would come over and bomb America and maybe Canada on the way, and so they put up a radar line, and this line that was along here, this broad swath here, was called Mid-Canada Line, also known as the McGill fence, because it was actually engineered here by the physics department back in the 50s under a guy named Gar Wooten, who got all these defense contracts, and he said all the people working in the Eaton building, which has been torn down to build the Long building. The Eaton building was put there by Lady Eaton because she was a friend of the chairman of the department for convention out of people. And Gar Wooten came along and said, "Wow, looking at the defense contracts you could get," picked out all the people who were doing that, and said, "You go sit in the old physics building, and we're going to do radar." That's where that book is John David Jackson. He's a professor here. He wrote that book. He was an expert on these things. But the point was, we can be proud or ashamed that McGill contributed this beautiful Mid-Canada line, which was like all 3 of those lines were essentially obsolete when they were finished. But this one was put together. It was very clever, relied on very clever ideas and technology and stuff, but was absolutely destroyed by migrating birds. And as soon as the migrating bird pack came through, they said, "We're being attacked." so that was a complete waste. So the Americans came in and saved us, as they will if you don't watch it again. But basically, the DEW line was largely financed by American, defense dollars and contracts to the phone companies and stuff. And they put in this huge line of of radar stations, and they put them in, you know, a time period that's unthinkable today. It was like 3 years they did it. And it's all done up in the polar night. They get sea lift everything up in the summertime, and they get to work and they parachute in bulldozers and stuff. Just crash program, worthy of the Manhattan Project. And they essentially obsolete, because by the time they finish it in 1957, people will be able to go off a nuclear bomb over the pole with the rocket. I always recommend this to every student I've ever seen. You've got to see this movie. This explains a lot of what runs our society. Beautiful movie. But the sad part of this is that a lot of the indigenous people came and were hired on to help build the stations, and it just essentially destroyed their society. They became wage earners. They became dependent on goods from the south, and you know, all it's lasting damage. And also, there's $1 billion thing that's still going on. You know, all the drums of fuel and things like that were just left there. You know, 'cause people go places. Go to an island, you bring stuff into the island, you never take it off. You know, you don't take an old junk car off an island because it costs money. You know, who's going to pay for that? Same thing with stuff in the Arctic. I'll see you later. And so this was anyway, Cambridge Bay. That's exactly why it's there. Okay, Resolute, same idea. It's a town built on the extraction industries, and lots of infrastructure for people exploring for diamonds and gold and uranium and precious metals up in the Arctic. This is us arriving in Resolute Bay. This is the first thing you see when you get out of the airport. Like, you know, somebody had an accident, they just left it there. You know, this is like, but this is where Frank Gehry was inspired to build some buildings and really. Just, you know, it's the contrast in the Arctic is just like beautiful nature, ugly where man has been. And hopefully some of that will be mitigated with some of our new Arctic policies. There's the Atco Hotel, which costs $450 a night, but you get dinner with it. You share a room with 3 or 4 other stinky guys coming in from the window. But this is where we stayed the first couple of nights. This is where some of the locals live, and like I said, nobody cleans anything up. But if you just leave town and just walk down by the river, you know, watching for polar bears and stuff, that's the kind of beauty you have. Okay, so then we went to Grise Fjord, which is Canada's most northerly permanent settlement, and we're taken there by a twin otter, which is the workhorse of the Canadian Arctic. Very short takeoff and landing, lots of capacity and carrying passengers. And I had met an electrician from Newfoundland who was on that flight. We met in the Resolute Bay Hotel, and he said, "Go and sit near the front." And he says, "Oh, you'll get a thrill." So I sat up near the front. This photograph doesn't do it justice, but to get into that airport, and one of the reasons we had to use the Twin Otter is because you come in and you're just about to hit the cliff, and you do a hard left and land on a 100-meter long airstrip. You know, so it is a bit of a thrill the first time you see it. Beautiful. I left out all the other photographs of the buildings, but the surroundings are magnificent. So finally we got to go. And we've been hampered by bad weather, you know, having been never getting the landing in a certain town, having to turn around. We finally got out to pick up our payload, and we had what the French call a grand beau. You know, it was just like absolutely stunning bluebird weather, and flew over some of the most magnificent territory I've ever seen, you know, from an airplane. And it's interesting. There's not a lot of snow, not a lot of ice. This is July, but you know, this is still the Arctic. There are glaciers, and you'll see some of that later on, but lots of erosion and just interesting geology. So we went out to get the payload, and this is where it was. It landed just nearby this little. It's not really a mountain. It's an outcrop, but it would have been very inconvenient if it was landed there, but it actually landed in a snowfield next to that, not too far away. But the cool thing was we were out there circling around. I don't know why I can't get rid of that upper thing. That means that it just got that. No. Okay. Anyway, what I'm trying to show you up on those sets of numbers is 78 degrees 7.53 minutes is not the same as 78.7 degrees. Okay, there's two ways to write down coordinates. One is decimal all the way, the other one is degrees in minutes. There's 60 minutes in a degree and not 100. And so somehow we had the coordinates in one system, and the pilots had misinterpreted and punched it in their system. We're searching around, where's and one of my colleagues got the bright idea, changing it to minutes. So there is, so we found this, $1 million payload, but it was like that. It was this is all upside down. These cardboard things are crush pads. They're, in the imagination of NASA scientists, the parachute comes down, and boom. No, that's how it ended up. So we got to work. We didn't know how long the weather was going to last, so we just jumped out of the aircraft and started. And Mike Sellers from Columbia facility, he has one tool, it's chop saw. When all you have is a hammer, everything looks like a nail. This is what he was. He was just part of the Texas chop saw massacre. And it was our job as the academics to keep him from doing that. We wanted him to do it, but we wanted him to, please spare this, please spare that. Meanwhile, Dennis, the graduate student, he was charged with getting this. This is a flight computer. It had 125 million events. That's all our data. If we couldn't recover that, game over. So we could have landed in a blizzard. I mean, we could have said, we're going out to get this thing, and it had bad weather and hurricane force winds and everything. That's the one thing we would have grabbed and said, we'll leave everything else. We can't replace that. So we got that. That was beautiful. And then we just started chopping cables and disconnecting everything. And the thing that I was up there to see was to get my aerogel back. And incredibly, I thought the whole thing would just come down and the thing would be powered. Because the number of tiles that you just leave on the desk in the lab and you look at it and it would crack or something. It was like really fragile stuff. We had started out with 50 tiles. We had 36 left to put in the device. And they survived the flight. They just really, and also the silicon photomultipliers, same thing. The most expensive part of our detector survived. So basically, we have the resources to start building the Phoenix, the thing that's going to fly again. And we piled as much as we could into the helicopter, flew home to Grise Fjord, and came back the next day. But we wanted to get everything out that in case the weather closed. But we got another beautiful day. I mean, it was really quite extraordinary. But what luck we had. And so we spent the next day turning the thing over. And this is where all of the stuff we bought in Canadian Tire came into hand. So we could sort of yank the thing and turn it over, and then get the superconducting magnet out and hook it up. And it was all taken out in two loads. There's the helicopter bringing it in. They brought the magnet down first, and then they went back and got the rest of the payload, dropped it down, and just to show off, they actually parked them so parallel to one another. It just made you want to weep, to see the precision of these guys. And so there we are, looking as smug as we can be. The magnificent 7-2 that did the recovery. And so we piled all the stuff into the Twin Otter that I came over on, and couldn't get the magnet in there, of course, but we got all the sort of bite-sized stuff. Just loaded the plane, loaded, and flew off to Resolute Bay. And we left these three gentlemen in the accommodation that Grise Fjord has, which is this rundown house, which I was happy to get away from. And we ended up in Resolute Bay. Instead of at the ATCO place, we found that there was the ATCO was fully booked up. We couldn't have found a bed there, but somebody had the bright idea to stay at what is called the Polar Shelf program, a building which the Canadian government has put up there. Essentially a giant building and a cafeteria and a gym and everything you could possibly want, and a fleet of Twin Otters across the road, where if you're a scientist and you have a project in the Arctic, my colleague Cynthia Chang takes her team up there every summer, and you can stay there, for nominal rates, because the government is supporting the idea of having scientific activity up there. And so we stayed there, and it was brilliant, except the internet kind of sucked. Meanwhile, our two friends from these guys come from Alberta and work in British Columbia. He's the pilot, he's the technician. You don't go anywhere in a helicopter, especially long distance, without having your own portable repairman. Because helicopters are so finicky, they have to be sort of every 5 hours of flying, you have to take them apart and put them back together, make sure everything is good. So these two guys were playing that role, and absolutely professional people. And they managed to get our two parts down in a couple of days, largely, I think, cheating on how long they were allowed to be in the air. I think they pushed the limits of their logbooks, but 24-hour sunlight is very helpful in that respect. And so now everything is clustered down at Resolute Bay. We got the biggest door in the Arctic. This is an Italian aerospace Airbus subsidiary, which produces these short takeoff and landing planes. So this one has a giant door that was specially put in for other reasons, but we could put the whole superconducting magnet and the rest of the payload inside, and we got all that in. Mike and I pretty much disassembled everything else into bite-sized pieces, and then it flew off. It came in 3 hours, load up, off it goes. Time is money. And then we said, okay, now we're going moons. No, you're not, because the Cessna, there's a phenomena. The other 3 flights were waiting in Sweden for launch, and they never got the conditions that people would sign off on. They kept saying, not today, it's a little windy up there. So they're all standing around, and finally, at the middle of July is when the season ends. You don't launch by the middle of the season of July, you can't go. They shut the whole thing down. So everybody at that week said, it's okay, we'll go. It's like, you say, what's the worst that can happen? I mean, when you want something to work perfectly, you wait till the perfect weather comes along, but when you want it to work at all, you just go with what they give you. So they all launched pretty much the same time and flew over and all landed in more sane places up near Yellowknife. But this Cessna, its #1 job is not transporting physics professors around the Arctic at high speeds. It's basically to go out there, and they have all this electronics on board to simulate if the command from Palestine, Texas doesn't blow the charges on the balloon to bring the payload down, they have to be there to do it locally. Plus, they're supposed to circle around underneath the balloon, because this, if you look on the flight recorder, if you look on the FlightAware website, you can see this whole area is covered with lines of airlines going from London to Seoul, from Paris to so lots and lots. And so these guys have to go out there and say the balloons don't have transponders on it, but the aircraft does. So this plane was booked up for a week, and we just had to tough it out. Mike and me. I got to know a lot about Trump supporters. Anyway, the bonus was, by the time they finally came and got us, the guys who had made it back ahead of us had packed everything up, so we just had to go home. Okay, so now we're back home. We've only got a couple of slides left. We've discovered that during the flight, even though we had the solar, we had white foam all around the payload to deflect some of the heating of the effects of the sun, we did get rather large temperatures in the payload, and that's going to make life difficult with the silicon folded multipliers. And then we have to do a lot of work with the drift chamber tracker. I mean, the drift velocities that are used, they're not constant with temperature. The thing is, in a lab, if you're working at CERN or a Triumph or something like that, you just take it for advantage. Take it for granted that everything is at room temperature, everything is controlled, humidity is whatever it is. When you're out here, the temperature is going up and down, and so all those things that you thought were constant but are actually temperature dependent, you have to take that into account. So it's taking a while to analyze the data, but I just want to show you one that's particularly dear to my heart. This is our checkerboard pattern of silicon fold multipliers, and it looks pretty. You can sort of see some rings on it in every one. And if you just do a time pattern, I have to say, I'm only going to take data that's really close to the time the positive ray actually went through. So many rings pop up. There's very little background. So the rich is working, and so that's a good time. And we're on our way to. And here's the propaganda poll. This is the one that we had to get ready for the summer conferences because it's really easy to make, but it looks so sexy. At least for me, I mean, it's kind of person. But you compute theta gamma, which is just a function of various velocities you get from time of flight. You measure the 2 times of the two big counters, and you get the time that takes it over T, and that gives you the velocity. So taking that velocity, you can compute this thing on the x-axis, and on the y-axis, you can say, how big was the signal? That's how much energy is dumped into the simulator to make the light. You plot one versus the other, and bingo, up comes your protons, your helium, your lithium, your beryllium. It's all there. Okay, like I said at the beginning, it's dead easy to measure elements. But there's our beryllium. We've got the beryllium. But now we'll say, which one is the beryllium 10, which one's the beryllium 9? That's where we got to get all the other stuff recognized. And that's going to be the, don't hold your breath, but you can, yeah, it'll come. So the future, I can see the future. We got 100 million events. And we have to calibrate them and we have to understand the systematics, but we're going to get papers out. And the first light has demonstrated the technology is sound and the experimental strategy is good. More flights are planned, but not yet scheduled. We need funding. We have to rebuild the gondola and solar array. We have to add a silicon tracker array to improve more momentum resolution. We're going to add more SIPMs to the rich and improve the cooling technology. And then we'll probably go back to Sweden. I think, we have a magnet which only keeps its helium for about 7 days. So doing a 55-day flight is not really necessary, but it would be nice to have like a 14-day flight because it's nice to have the magnet on for about half your day and then off for half the day, just so you can compare and you can do calibrations with the zero field stuff. Anyway, so we'll probably go to Sweden for the next one because it's just easier to get timed, easier to get launches. Longer term, we'll probably, if things go the way they do with other detectors, the next step would be a satellite detector. How do you get something out that doesn't need a replenishment of liquid helium? You rely on those same condensed matter people who were kicked out of the Eaton building all those years ago to invent room temperature superconductors that will give you a proper magnetic field that will last without liquid helium. And those things we're on the threshold of that. We're not too far away. So that's what we're going to try and do. Now, that's it. You just have to scan that and give me 4 stars.
We have maybe time for 1 or 2 questions from the audience. Yeah. And I ask you to repeat it just so that our audience can listen.
There no communication on the devices that have ones transmitted?
Oh yeah, it's on all the time. Now, so when it's in flight, NASA provides this big clunky heavy thing. We go to a great deal of trouble to make the thing light as hell, and then they load us up with all kinds of infrastructure on the same balloon. But they have a communication system which relies on relays off other satellites and things like this. But the cool thing is, there's also a thing called Starlink from a man who I will not mention, and we installed Starlink on the device, and it works like a charm, really good. And so all the data, we were downloading we couldn't download the whole data set, but we could sample the data set as time went on to see what the temperature was, to see if we should switch the high voltage down or something. So yeah, there's communication for sure.
But not enough data rate to put down data.
No, the bandwidth is not large enough. Yeah, and the other thing is that sometimes people ask, like, why don't you just steer it to where you want it to go? There's no steering on these things either. You're really relying on the fact that there's this natural vortex which sets up. It's not always there. It sets up during the summer, and we take advantage of it. But it's you can imagine why don't we put up a little propeller or something like that? You could probably work stuff like that out, but then it's all about power too. Like you can imagine certain schemes, and then you have to say no because it takes up too much power for the solar panels. But Starlink was really a game changer in this business.
Are you sure you're gonna get funding for the next?
No, well, I keep talking. We're having a group meeting actually here at McGill next week. And my colleagues are, I keep saying to them, did your budget get cut? And they said, well, no, we're on an extended budget from the original proposal. So we only have to find out next year if we have enough money to pay the postdocs and things. So yeah, but NASA seems to be more protected from Trump than the National Institute of Health and all that kind of flaky stuff that has to do with this. This is military grade research, right? Or something, I don't know, but it's yeah, NASA's not experienced a lot of disruption just yet, but things have changed a lot in the last year. Oh, and the other thing is actually, one thing I'm actually thrilled at is that you know, as a sort of the lone Canadian or the lone Canadian Institute on this very American dominated thing, I was happy to know that, the Canadians are getting into the game. I mean, they are starting to launch their own balloons out of Timmins, and they're collaborating with Europeans. And so there's actually a recovery going on. When we were up in Ellesmere, there were people in Baffin Island picking up the payload from a French / Canadian / maybe some other countries, having to do with atmospheric physics or something. It wasn't the kind of physics we do, but it was the idea that one of the things I like to emphasize is this is like it was when I was a grad student in particle physics, a group of maybe a dozen collaborators building your own detector, debugging and understanding most about everything in the detector, and getting it all done within the lifetime of a grad student or a postdoc. And now it's, you know, it's way out of control in things like mainstream particle physics, which is Large Hadron Collider stuff. But this is a way back into the kind of thrill of the early days and the pioneering efforts. So I think I'm glad to see Canada's getting interested in stuff like that.
If there are no more questions, we would like to thank Professor David for this awesome talk. I also would like to announce the winner of the raffle, the Maya, isn't it? He'll take one of the mugs off the table. And as I mentioned at the beginning, so our next talk, it's gonna be on October 29th. So we are gonna have 2 talks in October, just to make up for the one that didn't happen in September. And remaining fairly like with a similar topic, it's gonna be on Arctic climate change. So what is happening and why it matters. And it's gonna be a talk from a professor at McGill University. So join us, and if you're subscribed to our emails, you will receive some information about this topic. Again, I would like to thank again.
Thank you. Thanks for coming. Can I go? Leave the room? Oh, okay.
Just gonna, yeah, so
Yeah, do it gracefully.
Sorry, yeah, so I do not have a Mac, so
Yeah.
for me, like,